We're going to be talking about carboxylic acid and derivatives, and let's remember what is the order in reactivity of these compounds. So if we put here on the top the most reactive, we're going to have the acid halides. So typically here chlorides and bromides. So I'm going to put a chlorine for now. So all of the carboxylic acid derivatives are like this structure in general, where this group C contains an atom that is more electronegative than carbon. So that can be a nitrogen, an oxygen, a chlorine, and so on. So the most reactive of the series are the acid chloride or acid halides in general. Then we have the anhydrides. Then we have the esters. And lastly, we have the amides. In previous videos, we have discussed why is that, and it has to do, there are electronic factors such as electron withdrawing effects, for example, that makes the carbon more electrophilic. Remember, this is polarized this way, so that's delta positive, delta negative. That carbon is electrophilic. So when you have electron withdrawing groups, you make that carbon more electrophilic, but there's also resonance effects, and that lowers the reactivity, for example, in the case of amides. And that's, again, all that discussed in a different video. But now what I'm going to be using is this to predict products. And first thing we're going to be doing is describing, say, the two mechanisms that we will have in this problems related to carboxylic acid and derivatives. One is under basic condition and the other under acidic condition. So let's say under basic conditions, see, we're going to have, under basic condition, we're going to have say that I have acid chloride, so acetyl chloride for that matter. And say that I have a nucleophile under basic condition. Typically, we will have a species strong nucleophiles like that. So the first step that you're going to have is a nucleophilic attack over to the carbonyl carbon. That will form what we call a tetrahedral intermediate. And this is, here you're going to have nucleophile. I'm going to do just in general that. So this is tetrahedral intermediate because remember that here you have changed the hybridization in this carbon is sp2, and now in this product the hybridization is sp3, so tetrahedral geometry. So we call that a tetrahedral intermediate. Tetrahedral intermediate. So first step is nucleophilic attack, as we see here. The second step, you're going to reform the carbonyl group. And what's going to happen, you're going to have the loss of a leaving group. Your leaving group is excellent, is chloride, so minus chloride, let's say here. Then you're going to be forming the another carboxylic acid derivative from an acid chloride. Summarizing the steps under basic conditions are: step 1, I'm going to write Roman numbers here. Step 1, nucleophilic attack. And step 2, you're going to have the loss of leaving group. That's what happened in the second step. This mechanism is what we will have for most reactions that happen with acid chlorides and with anhydrides, being this the most reactive. So we're going to see that. Now, let's just do what is the general mechanism under acidic conditions. So under acidic conditions, then things happen, and we will have hydronium there. So I'm going to erase that and give you another example. So what's happening under acidic conditions? So, and I guess I'm going to squeeze that. So this is basic conditions. So acidic condition over here. Acidic This time I am going to start with a different compound. I'm going to say that I have an ester here as one of my derivatives. Under acidic condition, what you will have in the first place, I'm going to draw here acidic condition. Remember that we will have hydronium. So what's going to happen here is that this is, you're going to have the protonation, but where? Here you will have the protonation will happen at the carbonyl group. So, and you're going to form this intermediate. Here's formal positive here. That. So now, when you protonate the carbonyl oxygen, you're actually doing an acid catalysis because now you're making this carbon more electrophilic. If you think of the resonance structure here, and let's draw it to explain why is that more reactive once it's protonated. Once it is protonated, you will have the following. And this will have formal positive. So again, your structure obviously is a hybrid of that. So, but you're making the carbon more electrophilic, therefore more susceptible for a nucleophilic attack. So first step, we're going to say step 1 is a proton transfer. Where are you protonated? At the oxygen of the carbonyl. So next step you're going to have, and here I'm doing, say, an ester hydrolysis under acidic conditions. So I'm going to do my nucleophile is going to be water. And now removing this one, so that I have my arrows for the reaction. Now you're going to have OH, R, and now I'm going to have, this is now formal positive. I need to do a couple proton transfer steps. So here we have step 1, the main steps. Step 1, step 2 is nucleophilic attack. And that's another tetrahedral intermediate, but that's an oxonium. And what's going to happen, so I'm going to do 2 arrows proton transfer. I need to remove that proton here with water acting as base, and then I need to put protonate that. So after those 2 steps, I'm going to end up with this. Now it's formal positive here, and I'm gonna have OH. The next thing I'm doing is forming a carbonyl. So now I'm gonna have, this is the carbonyl, but now it's protonated. I'm gonna have OH, and that was R in R. So this is almost the carboxylic acid, so my final product. Again, we need another proton transfer step, proton transfer. And when you have acidic condition, the proton transfer step here is water acting as your base. So in this reaction, so there is a number of steps. That was formal positive. And now I am going to have, after that proton transfer step, E carboxylic acid. So notice that it looks longer, that path for acidic condition, because we have a series of proton transfer, but what's important is the first 2 steps. So under acidic conditions, I'm going to summarize. We're going to have first proton transfer. And it was just a step, protonating the carbonyl oxygen. And second, I'm going to have a nucleophilic attack. After that, I will have series of proton transfer step. But what is important that you remember is that we have the opposite order of steps. Under basic conditions, we have nucleophilic attack first. Typically here, strong nucleophiles, and then the loss of a leaving group. And here, all I have is proton transfer first, and then nucleophilic attack. Then after we did that, that's one tetrahedral intermediate. That's another tetrahedral intermediate, but we have had protons being removed here with water and then added here. There's hydronium, remember, here. And another, so we have actually 3 proton transfer steps after the nucleophilic attack. But that's the most important part, remembering that the order of those steps, particularly the nucleophilic attack, here is second, here is first step. With that, we should be able to predict the products of most reactions in this chapter.